Hello students, we are starting chapter 3, and in this video we're going to cover functional groups, which can explain reactivity, can explain how drugs work in the body, and then we're going to specifically look at alkanes. We're going to talk a little bit about constitutional isomers, and you need to focus on and even memorize certain types of branching groups and other chains and common names. This will be important for naming. So functional groups basically lend creativity and diversity to molecules. If we're only looking at carbons and hydrogens, we're looking at molecules that aren't particularly very reactive. Alkenes and alkynes can be reactive, and we have whole chapters on those reactive groups. But it also gets more interesting when we start adding in atoms like oxygen or nitrogen. Because of the electronegativity of these, that really changes the reactivity dramatically. When you have these sort of groups, we call those functional groups, and these functional groups are important to identify because they are going to react very similar across a variety of molecules. So the first group is the alcohol group, COH. This is the alcohol that you're familiar with in alcoholic beverages. That would be ethanol, for example, 2 carbons and an OH. Here are some other examples of different alcohols. A primary alcohol has an OH attached to a carbon. A secondary alcohol has an OH attached to a carbon that's attached to 2 carbons. Here's a phenol group, specifically off of a benzene ring, which is also called a phenyl group. Okay, so alcohol has a COH group. Be able to recognize that. However, if you have a carbonyl group, which is a CO double bond, you get what's called a carboxylic acid. So if you see this group, you cannot label it an alcohol because of this more electron withdrawing carbonyl group that allows for resonance throughout this molecule. It reacts very, very differently. One, this lends to an acidic H. Also, this carbon is partial positive, so this carbon can be reacted upon by a nucleophile. The other thing is an H next to a carbonyl group, an H off a carbon next to a carbonyl group can be acidic as well. Call these carboxylic acids. If you have the COC group, you can identify it here, just a carbon, oxygen, carbon. We call those ethers. If there's a carbonyl adjacent to an O with a C next to it, we call that an ester. Very different reactivity. Again, it has that carbonyl like the carboxylic acid. So you can envision the resonance within this molecule, partial positive on this carbon here, allowing for reactivity there. The next group is an amine, basically anything with a nitrogen next to a carbon. So here's a secondary amine. We have a primary amine here. Notice how we identify primary. It's just a nitrogen with only 1 carbon attached. Secondary amine has 2 carbons attached. Here we have what's called a pyridine group, which you don't need to know that name. If there's an adjacent carbonyl, similar to what we were doing in the previous examples, we call that an amide. This is present, this sort of amide group here, this amide bond here, that's present in amino acids. That's the main linker, linking amino acids to give protein chains. Okay, ketone has a carbonyl, but between 2 carbons. Acetone here is a classic example that's found in nail polish. Here are some other examples. If instead of a carbon you have an H, we call that an aldehyde. Here are a couple examples, a hydrogen next to the carbonyl here and here. Here I don't show it, but it's assumed in the bond line structure, it's the exact structure, you do have an H, methylene octet. I know that because there's no formal charge. Sulfide is a CSC, similar to an ether, And think about that. O and S are in the same group. So this is a type of ether, but with sulfur instead of oxygen, and a thiol, instead of an alcohol, it has an SH instead of an OH. The last group is an aromatic ring, which has a benzene ring in it. Okay, so your book is going to have a chart of these. Familiarize yourself with the groups. Also notice certain name endings. For an alkene, it ends in ene, ene, ethene, ethyne, if it's a triply bonded CC bond. What else? If you have an alcohol, you can name it so that the alcohol is given the OL at the end, so all. If you have a methyl group, which CH3 is, this becomes methanol. Here are the ethers, you just name each side, dimethyl ether in this case. Some other notable ones is your amine at the end, methylamine shown here. A nitrile is just a CN group, CN triply bonded. So here is ethane nitrile. Notice the carbon of the CN is included in the naming. 2 C's is the eth group, which you'll learn. Sulfide, similar to the ether, dimethyl sulfide. When you have a ketone, this is a long chain of 1, 2, 3 carbons, so it gets the prefix prop, like propane, but since you have a carbonyl, it's propanone, and it's specifically a ketone. If you have a carboxylic acid, you write oic acid. So there are 2 C's, so it becomes ethanoic acid. Okay, aromatics are a class of their own. And the example I previously gave was benzene, showing there's resonance around the ring. You could draw the hybrid structure where you have 1.5 bonds around the ring. There's a current. The electrons are delocalized throughout the ring. Each of these carbons is sp2 hybridized, so it's flat, it's planar. This allows for stacking. This is important for materials chemistry, where you can, for example, form graphite, so flat structures of carbon-based systems. Also, nanotubes will roll around itself. It'll be like a flat sheet, but then you roll around itself to give a nanotube. Okay, you can have larger rings with these sort of delocalization systems, and even quite large. So here's benzopyrene. You could play around here and move the bonds around the ring like you're drawing resonance structure. Then you could see how there is movement of electrons. Again, that movement is through the pi system, through those p orbitals. So think of this as flat and p orbitals sticking out towards you and away from you. You can also have aromaticity in some heteroatom containing ring systems. So to help you visualize that this is aromatic, you can move the double bonds around the ring, but it might also help to draw a resonance structure here, an N-N double bond, and then this pi bond breaking going to form a lone pair here. This is a fun one. This is theobromine, found in chocolate. Very similar structure to caffeine. It just has an extra methyl group. So I alluded to functional groups being important in, say, drugs, also all sorts of biochemical processes. The reason is that the way that cell signaling works in our bodies is that molecules, they'll bind receptors or bind enzymes, and those are made up of organic molecules, specifically proteins. So there is a certain geometry to them, a certain polarity to them. So these molecules fit and either activate or deactivate certain pathways. So here are a couple structures that I'm showing to just highlight some functional groups. Here's THC from cannabis. You have this OH group, so you have an alcohol off an aromatic ring. You have an ether. You have an alkene here. You have this long chain. Sometimes you have greasy pockets in, say, enzymes or receptors that certain groups will fit into. Here's a yellow jacket alarm pheromone. So if there is some stress, the yellow jacket will emit this pheromone to call out to its other hive members. If you've ever been stung by an ant, that actually hurts. It hurts me more than I always think it will. And that's either due to, say, a sort of acid like formic acid or some other acid. Sometimes they'll have another organic compound that will act as a venom. In this case, for the fire ant, it's this alkaloid here. And alkaloid is just a nitrogen containing ring. And this is a long chain, lipophilic chain, so fat loving chain here. This parentheses 9 means CH2 group is taken in 9 times. This is a really interesting one. This is called the spirocycle because you have a carbon and there are 2 rings. And this is histrionicotoxin. This is from the surface of the frog. It's actually used as a poison in certain tribes in Ecuador and Colombia. They coat the tip of an arrow to create a poison. And you can see a variety of functional groups here. You guys should be able to identify functional groups. So if I gave you the structure, you should say, oh, there's an alcohol. Here there's an amine, because if you want to go so far, you can say secondary amine. I'm not going to get that specific. Alkene, alkyne on both sides here. Okay, functional groups are super powerful in terms of drug discovery. I worked in the drug discovery business, so I was in the business of designing molecules, and one of the biggest things you do is you start with some main scaffold or template, and you start modifying groups, essentially functional groups or halides around the molecule. So this example of the discovery of aspirin is a classic example. The discovery of a version of aspirin dates way back to roughly 400 BC. Hippocrates wrote that willow leaves and bark relieved pains and fevers. So you can imagine how that came about, people chewing on maybe certain leaves and barks and then noticing an improvement in certain ailments. So it turns out that if you isolate certain molecules from this willow leaf or bark, you'll find salicylic acid as the active component. That is shown below here in the structure. This notice has a carboxylic acid group and an OH alcohol group. It has a main aromatic ring here, the benzene ring, as a core. Okay, so the one problem with salicylic acid, though, taking that, is that it can upset the stomach. One of the biggest drivers for drug discovery is to obviously produce effective medicines, but also medicines that don't have side effects. So late 1800s, Felix Hoffmann synthesizes a version of salicylic acid that is gentler on the stomach. What does he do? Classic drug discovery modification. He takes this OH group and he caps it. He may not have known that that alcohol group was a problem, but what I suspect is he tried a couple things. Maybe he modified that carboxylic acid to an ester, or maybe to an alcohol, and just made all sorts of different modifications to see what works without the side effects. So the new effective, gentler on the stomach version is what's sold today, aspirin. You still have the carboxylic acid, but the alcohol group was capped with an acetyl group and formed an ester. Okay, this segment of the video is now going into our first main category of organic compounds, alkanes. These are saturated hydrocarbons. What that means is you only have CC single bonds. If you have CC single bonds, then the number of H's are maximized as you fulfill octets. So you always end up with this formula, if you just have C's and H's, of CN H2N plus 2. For example, methane is CH4. Methane with 1 carbon, so N is 1, you get 1 C. And then if N is 1, 2 times 1 is 2, plus 2 is 4. And that's true. In methane, you have 4 H's. So when you see this formula, you know you have a saturated alkane. Notice certain heteroatoms can change that number of H's, like if I put an N in there, but oxygens, for example, won't change that. Halogens replace H's, so that could change that as well. Okay, Unsaturated refers to having pi bonds, a double or triple bond. Each of these result in 2 less H's in the formula. So if you have 1 pi bond, you should have a formula of CnH2n. Here are some examples. Stearic acid, this is a fatty acid with only saturated chain here. A monounsaturated fatty acid would be oleic acid with this double bond here. Polyunsaturated, more than one double bond or one unsaturation, linoleic acid is an example. So these are just examples of fatty acids. When you have double bonds, they can create kinks. These are on the same side of the double bond, so this forms what's called a cis alkene. And kinks don't necessarily sit as well in fatty tissues. Notice this is very lipophilic, like the fat sits in the tissues. These are also a handle for chemical reactivity, and these sorts of unsaturated fats can be metabolized a little bit better and be cleared from the body easier. That's why saturated fats are not as good for you, because they just get deposited and sit and are hard to exit the body. Let's look at some key straight chain normal alkanes given the N symbol for normal. That just means straight chain because there's branching. Methane, ethane, propane. All of these prefixes depend on how many carbons you have. Know these, memorize these in the box. So if I have a 6-carbon chain, it's hexane with this formula. And that group, hexyl. Know all of these because we'll be using groups like that. Ethyl group has a C2H5 group. And this is important because a lot of times we'll deal with ring systems or other chains, and we'll be putting, say, a propyl group off of it, and we need to identify those. There are different isomers. So the word iso is same. It's Greek for made of same parts. So constitutional isomers, know that name. They have the same molecular formula, but different connectivity. This gives rise to different branching. So I have my N-butane here, straight chain, but what if I put this methyl group here in the second carbon? I get this, 2-methylpropane, prop for 3 carbons in a row, and a methyl group in the 2 position. It also has a common name. I put the common names above. Its common name is isobutane. You can use the common name, but I absolutely need you to know the formal IUPAC names below. The naming will go through very soon. 5 in a row is N-pentane. With branching, you get 2-methylbutane and then 2,2-dimethylpropane. Know all of these alkyl groups. Pause this and take a look and study these. The last one you don't need to know, but I just wanted to show you. This is for you to practice. Isomers can result in different functional groups. So here are 2 isomers of C4H8O2. One has a carboxylic acid, the other is an ester. So here I could have taken this methyl group and just put it on this O here to give this compound. Same molecular formula. Notice that this formula is not CN2N plus 2. It's CN and 2N. That should have told you that you have 2 less H's, meaning you have some sort of unsaturation in the molecule. So you have, in our case, a double bond here. The other thing that you could have is a ring, because if you tie this up in a ring, you have to remove 2 H's from the molecule. So just to let you know, you could draw all sorts of different isomers of these. Maybe you have a double bond. It could be just a CC double bond, or you could tie it up in a ring, a variety of rings. So I want you guys to practice that and just see how many isomers you can draw. You can check your structures just by determining the molecular formula and see that you match. Okay, we're going to end here.